welcome you all to this course on diffraction and imaging. Today we will discuss about reciprocal lattice. Okay. So far in the last few classes we have discussed about how to use the information which is given in International Union of Crystallography to construct crystal structures, correct? So if you see here, we mentioned the lattice because generally this lattice is which is constructed for a Bravais lattice. Okay, for a Bravais lattice we construct a reciprocal lattice. The formula you use 2d sin theta equals lambda, right? Lambda is the wavelength of the radiation which we use it. Okay. What is it which decides the crystal structure? What is the value at which you get different peaks that corresponds to theta values or the sin theta, correct? So this sin theta will be nothing but lambda by 2, you can take it this 1 by d, correct? So our sin theta is proportional to 1 by d. What is 1 by d? D is in real space, correct? 1 by d is the reciprocal space. So whether you like it or not, every time you look at a diffraction pattern, either in TEM or in neutron diffraction or in X-ray diffraction, the information which you are getting it is actually in reciprocal space, right? So that is one more added incentive to learn about the reciprocal lattice. Okay. Then the other incentive is also is that when you look at the reciprocal, the way we represent a periodicity, okay, that is always we use a mathematical expression to represent it, right. So even for an electromagnetic wave, so when we represent it, we write it as e to the power of k dot r, we represent it, correct. This is how we represent an electromagnetic radiation, or I should not call it as a wave because actually wave is a misnomer. Essentially we should call it as any periodic fluctuation. Okay. We will represent it in this form. What is k? K is nothing but 1 by lambda, right. So again if you see, the momentum space is nothing but an inverse of the real space. Because of this, whenever we do a diffraction experiment, okay, if you have to derive a formula to find out how the scattering is taking place, what is the way we represent the incident ray probe? Incident probe, you represent it in terms of a expression like this, that is I is equal to exponential 2 pi I k dot r, right. So where the characteristic of the radiation is given by k, correct, which is in a reciprocal space. So when this wave interacts with that sample, and the wave is getting scattered, the scattered wave also, if you try to represent it, it is also again represented in a reciprocal space. So if you have to look at that interaction, if we can represent the sample also in a reciprocal space, then it becomes much easier to do this calculation rather than trying to represent it in a real space. Okay. Okay. Here what I have done is just shown a two-dimensional periodic lattice. Okay. Here with respect to an orthonormal coordinate system, these vectors A and B can be represented in this particular fashion, right. And then all these various vectors are nothing but what is going to be the translational periodicity in those directions in the lattice. That is what it represents, right now. This is for a two-dimensional lattice which I had considered. Okay. Three-dimensional lattice, we will be writing it an expression like this. Now let us look at the thought experiment. Suppose this is the position of atoms in not atoms, I should call it as a lattice, 2-dimensional lattice. The position of the lattice points are given. It is a rectangular lattice. This can be considered as like a real experiment. Like suppose we have a lot of flagpoles are being put for a Republic Day function. It is being arranged in a way periodic way, but it is like a rectangular arrangement. Suppose I wanted to photograph this, but each row I wanted to take a photograph. So, what are the options which I have? Two directions, means two directions, each row when I have to photograph it, I will have to move across this row from here to here, and every time I will have to click when I am right in front of this row, correct? That is the one way in which we can do it. Okay. I am considering as an experiment where I am moving on a vehicle, in which on a pole I had fixed the camera. Okay. The camera can only rotate around the pole, and whenever, if I can adjust the rotation of the camera around the pole in such a way that it moves from here to this position, when it reaches, the camera faces all these row of atoms. When it goes from here to here at a particular speed, we will be able to capture all the rows will be taken with at a particular time it will be taken, correct. If I try to plot the movement of the camera, how will it look like? How the camera has moved? With respect to distance. This is the way it will come, right? Because the camera is like this, it moves like this, it has to rotate around it. That is r and theta with which you can move the camera. But the camera is rotating around the axis, but this whole thing is moving, right? If I try to plot it, this is the sort of a periodic function with which we will be getting it. So, every time the camera reaches this particular, the crest of it in this particular position, then you are going to, it is going to click. Okay. So, this way I can get all the rows missing out any of the atoms, okay, in this direction, I can photograph it, correct. Am I right? Okay. This is exactly what has been done. So, if this wave has to be represented the way this is camera, we have to represent it in form of an expression. What is the sort of an expression which we will use? This is y is equal to a cos 2 pi x, and if b is the distance between them, this is the way an expression will come, correct. So, every time camera reaches this particular one, it is clicking the photograph because all other layer atom positions are just behind it. Like this, suppose instead of moving it parallel to this, suppose I am moving it in this direction, then what will happen? In that case, the distance which I will be travelling here will be much more, correct. That means that projection of this into this one has to be taken. That projection, if you try to take it, that will nothing but a dot product, correct. That is essentially what we write it as y equals a cos 2 pi, correct. This way we can consider it. Similarly, another experiment which we can think of is, suppose I am taking an electromagnetic radiation, okay, or a plane wave I am allowing to pass through. So, the plane wave as it moves, it has crust and trough like this, right. So, if we just mark, this is how the crust is going to be, okay. If that wave enters, as it moves, okay, if it has some wavelength lambda, okay, then if I start with a crust touching on this atom position, as it moves in this direction, okay, there is no need that the crust should come always there. What is the condition under which it will come? For the particular value of lambda, where the value of k is equal to, if this is the translation vector in this direction is r1, inverse of that, correct. So, there is a specific value of lambda at which it will occur, right. This way, by putting a wave like this, I can get all the atom positions the crust making fall, right. The same thing which I can do it in another direction. In this direction if I take, what should be the wavelength of the radiation? It should be some other value, so that okay, as the wave passes through, all the crust comes right on top of each of the lattice position in that direction. That is 1 by r will be the in that one. That is the way the expression will turn out to be, right. Otherwise, in the direct lattice if we see that when the crust from one to the other, it will be the distance here in this case r2, but when we express it as a wave, okay, the property of how we mathematically express it, it is only the k which represents the wave and a represents the scattering from the interaction, the strength of the radiation, correct. These are all the two factors which define the radiation which is entering. Exactly that same thing is what we are doing it here also, okay. So, if we do this, now how do we represent it? Okay. Suppose I choose some particular point here, okay, like here I mark a point here. Okay. From this point, which is the point at which an identical position will come if I am moving in this direction, maybe from somewhere here, right. How will we represent these 2 points? Will be represented as e to the power of I 2 pi. Okay. Now, k I am choosing it as a specific value because that is the value with which we are choosing the radiation. Then k dot 1 is r plus r, right. From an origin which you have chosen, this point is at r and another this point is r plus r, okay, because this distance is a vector r. Okay. Then the expression turns out to be should be equal to e to the power of I 2 pi k dot r. This is what it will turn out to be. So, this will finally lead to a condition k dot r should be equal to 1, correct. So, this is one of the most significant expression which we have to consider as far as a reciprocal lattice is concerned. Okay. So, if this value has to become 1, okay, what should be the value of k dot r? This factor? What? Not 0, it can be any integer including 0. It can be positive, negative, any value it can take, right. This is a value which is possible, correct. So, then for all those values, that is if you take k dot r equals 1, also this will be 1, na? K dot r 0 also will be 1, minus also and also it does not matter what the value is, but this has to be an integer. Okay. This is clear. Okay. Now, suppose we are considering this with respect to particular some specific r value we choose it here. Okay. Generally, how do we represent the direction in a lattice? Okay. n1 into A plus n2 into B plus n3 into C. This is the way we can write it, right. If I substitute it here, then what this expression will become? That is k dot this should become n1 into k dot A plus n2 into k dot B plus n3 into k dot C, correct. And this has to become, suppose I write it as a constant m, okay. if this value m has to be an integer, it has to be an integer for all values, all independent values. That means that since n1, n2, n3 is an integer in the lattice, these 3 terms have to be an integer independent, each one of them individually has to become an integer. So, that means that k dot a, I just write it as an integer h, okay. K dot b, k, k dot c is equal to L, okay. This way we can write in some integer, we do not know what the value is. So, our aim is to find out now what should be the value of k, correct. That is what we have to derive, because this k is some vector in a reciprocal space, right. How does it related to the real space, that information we have to get it. What we can do it is that k, since it is a vector, okay, we can write k as equal to k1 plus k2 plus k3. These are all the components in I into this one modulus of k1 it will turn out to be, right, the x, y and z direction. This way we can write it, okay. Suppose we wanted to find out what k1, k2, k3 is. Since we know the axis which we have chosen here, or suppose we draw it like this, and this is A and this is B and this is the C axis of the crystal whatever you have chosen unit cell. Then the BC plane is going to be the one which is in the A axis direction, correct, okay. Is it not? If I take a vector product of B cross C, what does it denote? A vector normal to that plane, BC plane, that is vector normal to the 0, 0, 1 plane it gives it, right. So, that will turn out to be, that is I can write k1 to be equal to some constant into B cross C, but we do not know what the value of alpha is, right. Similarly, k2 can be written as beta into C cross A, k3 can be written as gamma into A cross B, okay. We are doing this exercise to find out what is the relationship between reciprocal and real space, okay. This okay. So, now this vector if we write it, this vector k will be into A cross B, correct. Now, if I substitute this k in here, now what it will turn out to be? If I take the dot product with respect to this k, it will be alpha into B cross C dot A will turn out to be H, correct. This is the sort of an expression we will get it. Beta will be beta into C cross A, B will be equal to k, gamma into A cross B dot C will be equal to H L. From this we have got alpha, beta, all these expressions which we have got it, value of. So, alpha equals H by A dot B cross C, right. Beta equals k by C cross A into B, gamma equals L by, right. These expressions are right. So, this what? If we substitute this into this expression for k, now what it becomes? K becomes H by A dot B cross C, right, into B cross C K into C cross A by C cross B L into A cross B dot C, correct? Is it not? If I, because what this value is only nothing but the alpha value which you have found, it is the magnitude. Now, so this is, we can take it as Ka, Kb, Kc, or we can write it as, this itself can be written as, if I write it as star B cross C, correct? Similarly, I am just denoting it this way. So, using this simple relationship that k dot r has to be an integer, okay, right? We have just derived an expression for what is the relationship between k, we have derived, right? And the k is nothing but, it will be h into A star plus k into B star plus L into C star. This is a vector in the reciprocal lattice, correct? H, K, L are the coefficients of that vector. Right? If you look at this vector, the definition, it is essentially with an orthonormal axis. Both the coordinate systems are the same coordinate system with which all the vectors are derived, right, represented. Is this clear? So, naturally, that is for every vector you can have a reciprocal vector. This is actually in vector algebra, it is called as a dual space, where for every space in a vector there is a reciprocal space which is always going to exist. Okay. That is apart from this. So, now what you can make out is that if the vectors in the real lattice exhibit whatever is the symmetry, the same symmetry will be exhibited by the lattice which is generated by using these vectors. So, the reciprocal lattice and the real lattice exhibit all the symmetry of the crystal structures, okay, but one is expressed in a real lattice, but the same symmetry everything is exhibited by. So, what does it mean? That is, when we put a sample which exhibits some symmetry, the experimental information which we collected also exhibits the complete symmetry, but it is expressed in a reciprocal space, correct? The information comes in that space, it exhibits it. So, if we analyze and get information about what we get it in the reciprocal space, we can immediately find out information about the crystal structure in real space. Okay? That is what the game is, but it is easier said than done. So, there are so many people who have worked on it, millions of scientists on various aspects of it. That I think possibly some of you also may be working on this in future. What is the other property of it? The consequence of it is that A star dot A will be equal to 1, equal to B star dot B, equal to C star dot C, correct? Similarly, A star dot B equals B star dot C, okay. These are all will be equal to 0, correct? These expressions, having got this equation, now you can substitute, okay, and just check all these expressions, okay. That I will leave it as a problem for you to work out, then you will understand how it comes, okay. Then another one is that, yes, Venkatesh.
Second condition, A star dot B and A star dot C.
C.
Is it 0
It has
if
to
we begin with the real lattice as orthonormal?
No.
We took it perpendicular.
No,
Or the
no,
real-
need not be.
ABC.
ABC need not be. Can be any value. It is an orthonormal system in which we are representing these vectors A, B and C. Okay? But the vector algebra, if you choose any vector A and B, you define it, that all the expressions whatever we derive all are valid. Okay? And what we do it is that one thing one should remember is that we have used here the shortest translation vectors are essentially a primitive lattice which we have considered. The reciprocal lattice is constructed for the primitive lattice of the structure. That is how it is always derived. Okay? So, this expression, see it is something like this. What is A star? A star contains a term B cross C, right? B star, that is B cross C if you take it, and that vector it will be always perpendicular, correct? So, that is what will happen to a dot product if you take with respect to B, they are perpendicular to each other, so that is 0. That is what essentially it means. Okay. This has nothing to do with that coordinate system. Okay. Now, what does this mean? Okay. If this k dot r equals m, again I come back to it because one should fully understand what the significance of this. That equals m means that if I choose a particular vector in the real lattice R, okay, there can be many values of k for which this equation will be satisfied. Or suppose I choose a specific value of k, okay, some particular vector I choose it to be k1, that k1 dot r equals m I take it, right. What all can k1 dot r could be equal to 0, k1 dot r could be equal to plus minus any number 1, 2 like that it can happen. Is it not? K1 remains the same. So many values of r which we can choose it. Let us just take that case k1 dot r equals 0. What does it mean? For a particular value of k1 which has been chosen, what is k1? K1 is normal to a particular plane, right? Plane normal, okay? But that vector with the magnitude which is inverse of the interparticle spacing between those planes, right? So, if I take a plane like this and suppose this is k1, okay, then there can be many atoms in this plane should be there, na? With vectors from here to here, okay, if I consider this as a plane which comes like this, okay, and this is what the vector k1 is. So, there can be many positions, periodic positions should be there. These are all, if this is the origin with r1, r2, r3 like this, so many vectors are there. Okay. All these vectors are perpendicular to that k1. K1 is only one vector in reciprocal space. To that vector there are many periodic distances are there. Okay. So, when k1 dot r equals 0 means that all the values of r which represent is a plane which passes through the origin and which is perpendicular to k1. That is the plane which it represents. Like for example, suppose I take a simple cubic lattice. Okay. I can have a plane which is like this. This is one on one plane, right? There can be an one on one plane that can be like this. One on one plane can pass through this. Another one on one plane can pass through this origin also. That particular condition represents the plane which is passing through the origin. Is it clear? Okay. what does K1 dot R equals 1 represent? Okay.
Parallel.
It will represent a plane which is parallel to it, nearest to it. All the atoms in that plane are the ones will satisfy that condition for the same K1, right. Similarly, K1 dot K2 will represent the third plane like this. So, like that, now if you look at it, almost all the lattice planes which are in that particular direction sitting one on top of the other, okay. If we represent that by a vector, okay, lattice translation vector with respect to an origin, the dot product, if we take it with respect to the reciprocal particular reciprocal lattice vector, that satisfies this equation. Okay. So, the entire lattice points have been covered now, is it not? So, this expression, this is equivalent to, any doubt? Okay, this is equivalent to, suppose I have a, take a plane like this, okay. This is a point R, okay, in the real space, okay, and this is from here I take it, suppose this OM is going to be the K1, okay. If I take this R, K1 dot R cos theta will represent some value, na? That is essentially nothing but projection of it into this one. If that turns out to be an integer also, this satisfies that. So, essentially on various planes we can have atoms which are there, all of them can satisfy this equation. Yes.
So, where you were explaining 1, 1, 1 planes,
Yes.
that actually that's not passing from origin. So, how we can,
Like this, what I can do it is that instead of taking at this plane, I can take a plane which may be inclined like this. This plane also is a plane which is there, okay. There can be another plane which passes through this. There can be a plane which passes through the origin, like that so many planes will be there, na? With respect, that will correspond to another K1 value, K value, okay. In that way also, if you consider it, for that specific value of K1, okay, almost all the atoms which are there on various planes, okay, they will satisfy this condition. So, this is the condition which has to be satisfied between the real lattice and the reciprocal lattice. You understand that? So, what this meaning of each of this expression means is nothing but with respect to a particular reciprocal lattice which vector which we have chosen, all the other vectors which are going to be there on different planes in the real lattice, they satisfy this condition K dot R equal to M, which is an K dot R equal to an integer. Okay. Is it clear? This is the most significant aspect of the reciprocal lattice.
so is the origin same for both real?
Origin is the same with respect to same origin. That's why I said that we are choosing an orthonormal axis system, with which initially when we started we are choosing with respect to this and orthonormal using this coordinate system we are defining A and B, right. Similarly, A star and B star also when we define, it is defined with respect to the same coordinate system. Okay. Only thing but what happens is that the coefficient of them of these vectors or these lattice translation vectors will be one is inverse of the other. You understand that? So, what we have tried to do is just try to find out what is the meaning for these k vectors, under what condition, okay, we can generate a reciprocal lattice. So, using these expressions we can generate a reciprocal lattice for a real lattice given a lattice parameters A, B and C. There are many conditions which we can, that is this same reciprocal lattice, suppose it is going to be a triclinic lattice. if it is going to be a tetragonal lattice. All of them, I think I will make you do as an exercise so that you understand how the reciprocal lattice comes. So, essentially what one has to do, if the lattice is a primitive lattice, okay, like simple cubic system is a primitive one, okay. We know where the A, B and C parameters are known. Now, suppose we take a body centered lattice, then what we have to do? We have to first find out the primitive lattice vectors, okay. That primitive lattice vectors in the last classes in the regular, this one we have seen that it will be like one vector could be, it will be A by 2, one is I plus j plus k, right. The vectors, another will be I plus j minus k. There are 4 vectors will come off this one. We will choose 3 of them to define that coordinates, okay. And now when we know these vectors A, B and C, this is A, this is B and C if we know, then using this expression we can find out the reciprocal lattice vectors, okay. Then we can draw a unit cell corresponding to that. That is what we find, that when you try to create a unit cell in reciprocal space for a BCC unit cell like FCC, and FCC unit cell resembles like BCC, correct. Simple cubic will look like. So, but for others there will be some rotation also will be there. That is why I would like you people to do some assignments looking at non-cubic systems, okay. Then you will understand this reciprocal lattice concept, how to do it. This is one to construct it, and then another is that since we know the planes which we are taking it, the vector which is perpendicular to that, with respect to that now we can index each reciprocal lattice vector represents a particular plane in the lattice, correct. So, that point, if a plane we index it as HKL, then the reciprocal lattice point also we can index it as HKL, right. That is the way we can represent it, okay. And since we are choosing a primitive lattice, okay, what is the advantage of using a primitive lattice? That is, when you look at the extinction condition, which will come to later, is that there is no none of the points are missed, because all lattice points are scanned here, okay. Naturally it takes care of the extinction condition when you construct a reciprocal lattice, okay. If this will come to know itself, what we will do it is that this is a mathematical expression way in which we have to draw a reciprocal lattice, we have looked at it, correct. That is B, that is another vector could be A by 2 I minus j plus k, A by 2 minus I plus j plus k. These are all nothing but 3 vectors which are one on one vectors which you are taking it, that generates the rhombohedral lattice, correct. Okay, we will come back to it later, okay. Suppose we have to construct this, what is the geometrical way in which we can construct a reciprocal lattice? This is the same mathematical operation, we can do it also, okay. Mathematical way is the most elegant way of looking at it, okay. This is what the law which is called as a reciprocal law, that is for every set of direct lattice planes corresponds to each set of a direct lattice planes corresponds to a reciprocal vector, lattice vector. Similarly, for each set of a reciprocal lattice planes, there corresponds one direct vector, okay. That is all a different way of interpreting the same expression k dot r should be equal to an integer. What does this essentially mean? All these expressions which we have taken are here, B cross C by, this can be considered like, suppose we take I do not know whether I have drawn it correctly or not. Yeah, it is okay. A, B and C. What does A cross B mean? It is AB, the angle between them sin theta, correct? Physically that is what it means. Nah? That we considered in a vector algebra as a vector which is perpendicular to it. Actually what that magnitude is nothing but area of this parallelogram, correct? And what is, and that is what we define it as a vector in this direction A cross B, correct? What does this dot C means? That it is nothing but projection of C onto A cross B. The projection of C will be nothing but C, if this angle is theta, C cos theta, correct? This C cos theta angle is nothing but the perpendicular distance between the planes, correct? Is it not? C cos theta is nothing but the perpendicular distance between the two planes which we are considering it. Okay. That is the area multiplied by the perpendicular distance vector algebra. If you take this vector A cross B, okay, divided by the volume is, what are we doing? Area divided by volume, you put it, is nothing but inverse of the height, but the direction is that same. So it is in the direction which is perpendicular to that whatever the planes which are there, that height which we are taking, correct? Is it not? This is exactly what is being done by all these vector algebra operation. The same thing we can do it on any crystal structure, correct? Let us just try that. Suppose we take this is a lattice, okay. You take an origin from here, this is A and this is B, okay. So these are all the A planes, correct? Is it not? And consider that this is C which is perpendicular to the board. So is it clear? You can work it out later, okay. Suppose this is a vector A, these are all the planes which are going to be there, these are also, this will be a 1 0 0 plane, this will be 2 0 0 plane, this will be 1 bar 0 0, correct? Like that these planes will go, because this is where the planes are which are in the C direction, and these planes will be 1 0 0, okay. No, 1 0 0 family of planes will come in this, okay. These are all the family of planes, okay. 2 0 0 plane cannot come here, 2 0 0 plane has to come half distance, sorry, okay. 1 bar 0 0, this will be 1 0 0 plane, correct. Now this is a primitive lattice. What is the plane normal here with respect to this one? This is going to be the plane normal to this set of planes, correct. To this set of planes like this, the plane normal is going to be in this direction, is it not? Because this is the plane, this is the plane, the normal to it will be vector will come like this. That is how the plane normal will be with respect to, this is 0 1 0, correct. Is that clear? This way we will draw a plane normal. So see, this is, if this is A and B are the vectors, okay, this is in 1 0 0 direction, this is 0 1 0 direction, this is a parallelogram, 2 dimensional, this is 1 0 0 type of planes, family of planes which are there parallel to this one BC planes, correct. Similarly, the planes which are parallel to this will be 0 1 0 planes. The planes which are parallel to this at specific distance along C will turn out to be the 0 0 1 plane. because you are always thinking with respect to cubic system. So you are thinking that it has to be perpendicular, it is not.
Is this the top view?
Hmm?
Are we looking in top?
No, here what we are doing it here is I am just showing only a two-dimensional lattice. If we construct as a three-dimensional lattice, like suppose you assume it is to be a monoclinic system, I can take the next plane will be kept on top of this, correct? If you just consider only a two-dimensional lattice, there are only, this is one set of, and three-dimensional lattice, if you consider it, this is a set of plane, this is a set of plane, correct? With respect to this plane, what is going to be the normal to it? To this set of planes, this is going to be the normal. That is what you have learnt in the real structure is that the vector which represents the direction and the planes which has the same Miller indices, they are plane normal if you consider it, they are not in the same direction, correct? That is exactly what we are doing it. So, the between these, if you wanted to find out an interplanar distance, I will have to draw a perpendicular vector. Na? Similarly, to find out the spacing between these in this direction, essentially this plane is the perpendicular vector. In this vector, if I take a distance and suppose this distance is the d010, okay, 0 1 0 0, and in this one is d100, okay, and if I take the inverse of that distance and mark it on that, okay, then what it will happen, A star will be equal to 1 by d 100, okay, this is the magnitude. B star will be equal to 1 by d 010. D is nothing but the interparticle distance. Okay. So now if I try to draw this with respect to these vectors which I have taken, okay, here when the plane separation is short, the inverse of it will be large, correct? So the vector which we mark as A star here will be proportionately larger, and the vector which we mark as B star will be proportionately less. Now this by vector addition we can generate all other points, right? So that way now we can generate the reciprocal lattice for this two-dimensional lattice. This is how geometrically we draw it, okay. And in this what we have done it is that, which one should always remember is that we have to draw everything with respect to a primitive lattice, correct. Suppose in this particular lattice there is another lattice point here, then what will happen? The family of planes, one plane will come here, na? Then the separation between the planes is not this, it is this separation, the distance. So that is why I said that it automatically takes care of, when you take a primitive lattice, it will take care of the factor is taken care of. Okay. So this is how you can draw a simple reciprocal lattice. That is what essentially is shown here. Draw plane normals, okay. All the planes you can draw the normals and then find out the reciprocal distance and mark it, okay. You have done it. This and the mathematical expression which we have derived is essentially one and the same. We are only implementing the mathematical expression in this form geometrically. So geometrical way we can construct it. But the problem which happens in geometrical way is that again in a three-dimensional structure if you wanted to do, it becomes a little bit more complicated because visualization everything is necessary, correct. Whereas when we do it with a mathematical operation, from that reconstruction of a lattice is much more simpler. So that is essentially what is being shown here is the different type of lattices, okay. This is for a parallelogram, how the reciprocal lattice vector look like. But what you should understand is that these are all, when the reciprocal lattice unit cell, if you look at it, this unit cell is an exaggerated size, because the distance is an inverse of it, but it is in a space, it is an inverse distance, correct. So, you can choose some scaling factor to plot it so that it is observable to us. Okay. What is essentially important is that taking the, like if you, when you try to find out the volume of the lattice in the real lattice, it is A dot B cross C, right. That volume depends upon what is the unit which we choose to represent A, B and C, correct. Similarly, if you take the reciprocal lattice unit cell also, we can find out what the volume is. There the units are going to be inverse of that distance, whether it is a millimeter or a centimeter or a nanometer, inverse of that is what which you have to take it. If we take the product of these two reciprocal lattices, this we can work it out as a problem that it will be turning out to be 1. That is volume in real space and volume in reciprocal space of the unit cell, respective unit cells. If you consider, that product is always going to be 1. Okay. So, this is the one way in which geometrically, this also what we will do it is that this time we will have in a real lattice how to construct a lattice. Next week we will consider how to construct a reciprocal lattice, okay. So that it will become quite clear how reciprocal lattice can be constructed for any of the Bravais lattices. Is it clear? That one should become quite familiar with it. Then it is very easy to understand diffraction pattern and all from various crystal structures. Okay. So, this is for the 5 planar lattices are there, right. You see this one which I have taken from the book, is these two correct? This is the real lattice, this is the reciprocal lattice vector. Are you sure? See, this normal should have come like this, right, to these planes. Normal should be here. Is it taken that way? Yeah, correct. Yeah, correct. This one, and normal to this should come. Yeah, right. So similarly, if you take a rectangular lattice, how it will be? Okay. Here it is elongation is in this one. It will be in the perpendicular direction. It will turn out to be. Okay. This is how various reciprocal lattice will appear. Okay. So if we take the lattice, the third dimension also, then we can construct a reciprocal lattice unit cell. That is what it has been constructed for a monoclinic system. Okay. But what is essentially important is that this is one layer, this is another layer which is being put on top of each other. Okay. This is how the monoclinic reciprocal lattice has been generated. Similarly, one can try to work out for reciprocal lattice for cubic systems also, cubic and non-cubic system, which I think I will give you some assignments to work, which you can try it, and then we will have class also, okay, special class where we will you will try to work it out in the class. Then it will become quite clear how these reciprocal lattices can be constructed. Here just I have shown some with some examples reciprocal lattice for a like for example, we started initially with a cubic system, right. This is a body centered lattice, okay, BCC, for which with respect to this point, when we try to draw the rhombohedron, that is a primitive lattice, this is one vector, this is another vector, okay, and this is going to be the third vector. Okay. How we take these 3 vectors, these are all the coordinates of these vectors. Okay. If we try to use vector algebra, then you will find that A star, B star and C star will turn out to be of this type. Okay. Then one can draw the full reciprocal lattice unit cell. Then if you look at the reciprocal lattice unit, what are symmetries which it exhibits all the symmetry of the real lattice will be exhibited by the reciprocal lattice also. And here if you see it, automatically when you look at some of the reflections, like here 200 reflection is present, right, 100 reflection is automatically becomes absent, because the reciprocal lattice is constructed for a primitive lattice. Similarly, here what I have done it is that, how will you find out interplanar distance in a vector notation? This will be AB into V, divided by A cross B the whole square. That is how it will turn out to be. So, if we summarize, what have we done in today's class? What is the way in which real lattice, the position in the real lattice can be represented mathematically. That is in a vectorial form. If we represent it, we generally represent it as R equals N3 into C, correct? The another form in which it can be represented as a periodic function, if you try to represent it, then it has to be represented in the form of exponential k dot r should be equal to 1, where r represents the real lattice vector. Then we try to find out what should be the values of k. What is the relationship between the real lattice vector and the reciprocal lattice vector? So, reciprocal lattice vector essentially represents nothing but planes in real lattice, and then how to construct these lattices just for a 2-dimensional lattice parallelogram. We have considered how to draw a reciprocal lattice geometrically. Both are essentially an equivalent one, and in fact in this equation normally what we write, R is equal to R equals U into A plus V into B plus W into C, correct? That is how it is represented. And then K we represent it as H into A star plus K into B star plus L into C star, correct? If you take that K dot R, what it will turn out to be? It will turn out to be HU plus KV plus LW, right? This turns out to be N. You will be all familiar with this equation, which you called as the Sohn law, right? Sohn law is also nothing but a relationship between a real lattice and a reciprocal lattice. The reason for this is because whenever we use HKL, whether we are aware of it or not, when we use HKL to represent the planes, it is nothing but using inherently a reciprocal lattice vector is being used, because HKL are nothing but coefficients of reciprocal lattice vector. That is why this expression it turns out to be. This expression normally when it equals 0 is the one which we always say that Sohn law, but generally, that is, if we use this law to look at different reciprocal lattice planes, if you are able to get that information, the complete crystal structure information will be available from the 3-dimensional lattice. That is, the Bravais lattice can be reconstructed from this. We will stop here now.